You got two on the bottom
Yeah, two on top.
and two on the top, two on the top, two on the bottom. Is that what you got? Well, it depends. If you count, this is 7 electrons. If you count 8 electrons, you got 8 electrons or 7 electrons? 8 electrons. How many did you get, Cody? 7 electrons or 8 electrons? 7. Okay, so we have nitrogen with 5, and then 2 hydrogens. That gives us 2. Did you count the negative charge?
No, I didn't.
Yeah, the negative 1 charge means we have to have 1 extra electron. And so that gives us 8. And so it should be 2 dots on the bottom here. That's good. This would be the correct Lewis structure for that. The amidon, where the dots are, is important, but not in Lewis structures. In Lewis structures, we just want to look at how the bonding arrangement is. We don't care about what's called the geometry or the shape of it. And so the Lewis structure need not conform to the actual position of everything. And so wherever you throw it is fine, because what we do is we do a separate analysis for shape and geometry. In fact, if we're looking at the shape of this one, the shape of the ammonium molecule looks a lot like methane. Actually, let's take a look at that right now. If we do, the shape or the what we call the geometry. Here, oops, that's not so easy to see, but here they're trying to kind of show the shape of this on a flat piece of paper. And so this is ammonium positive charge. What they're showing is this line is in the plane of the paper. This is a wedge. This wedge sticks out. These dashes stick in. So we've got 2 dashes sticking in, a wedge sticking out, and this in the plane. And so it has this shape. This is a very familiar shape to chemists. Do you know what chemists call this shape? Tetrahedral. This is a tetrahedral shape. Methane's just like this. If you look at the shape of methane, it's just like that. And so ammonium has the same shape as methane. Here's another one. They did this one oriented differently. Actually, both of these two were exactly the same, except they just rotated the molecule a little bit. They rotated the molecule a little bit to put these 2 bonds in the plane. This wedge sticking out, this dash going in. It's a tetrahedral also. And just different ways of visualizing tetrahedral. This is a ball and stick. If you look at it in terms of Lewis structure, it doesn't look anything like that, because Lewis structure we don't care. We just want to see how the bonds are what's bonded to each other. But when we're interested in the geometry, we want to know, like, this is called the angle, bond angle. This is tetrahedral. It's ammonium as well. Here's another one. This is the classic way. This is the most common way it's drawn. The most common, well, actually, the most common way it's drawn is flipped 180. And so we have bond here, a bond coming out here, a wedge coming out here, and a dash going in here. The most common is flipped 180. This is not tetrahedral. This is tetrahedral. This is tetrahedral. Oh, this is one with shadows here. You see that? Here, this is the most common way it's drawn. Do you see the top left? Yeah. And this is flipped 180 from that. Tetrahedral. Look at where they put the formal charge. This one indicates the formal charge. Do you see the formal charge? Circle on the nitrogen. This is this looks like a quantum mechanical calculation. They got some data here, hard data. Here they didn't circle the formal charge. Usually it's circled. Here's the net charge. They're not showing any formal charges here, just the net charge. There's ammonia, there's ammonium. It's called a tetrahedral. Do you know why it's called tetrahedral? There's a tetrahedron is a four-sided polygon. And so do you see the red polygon here has four sides? That's a tetrahedron. So it kind of fits. This ammonium also fits in that tetrahedron there. Or it's tetrahedral. This, does that look tetrahedral to you? No, but Lewis structures don't matter. Uh-huh.
Does every tetrahedral have a 109.5 degree difference?
Yeah. Every perfect tetrahedral. Sometimes you put different things on there and it distorts a little bit, but not much. Like for example, this is different. This looks tetrahedral, right?
Yeah.
Except this is a pair of electrons, so it distorts things a little bit. This is ammonia, not ammonium. Yeah, it's just different. It's wrong. So those are some examples of that. If we look at ammonia, ammonia has a different shape to it. Let's take a look at the shape of ammonia. Next. Shape of the shape of for ammonia we don't call tetrahedral, even though it kind of looks tetrahedral, because the shape is going to be dictated by the atoms. And this shape is called trigonal pyramidal. It's like it's got a triangle base and it's a pyramid of atoms. The electrons don't count, so it would be tetrahedral if we counted the electrons, but in terms of molecular shape, no. But the electrons are there, so it forces those others down. That's trigonal. This is not exactly correct. This is just trying to show the shape, but the problem with this wiki is this line is supposed to represent 2 electrons, and that's 2 electrons plus another 2 electrons is 4 electrons. It's not right, because normally you don't do it. And so this line just represents where that pair would be, and it's kind of tetrahedral. But when we look at the actual shape of the molecule, the atoms are going to adopt the triangular pyramidal shape, so we can fit the atoms into that. That tetrahedral shape we call the electron shape. Here it is. This trigonal pyramidal. Do you see that? Wedge dash. Trigonal pyramidal. Flip the other way. Trigonal pyramidal. This is what we're talking about here. When we look at all the electrons fit in a tetrahedral, but when we look at just the atoms fit in a trigonal pyramidal. And normally when we're looking at molecules, we're just looking at the atoms. Trigonal pyramidal is it. A trigonal pyramid is this stuff. So when we draw the Lewis structure, do you see trigonal pyramidal at all in this Lewis structure? No, you don't care. Lewis structure. This one on the left is no good. What's missing on the left? Yeah, 2 electrons, so it's no good. This is what the shape looks out of a computer. Do you see the electrons? No, you don't. You just see the atoms here. The electrons are there. You can visualize them, but they're not being visualized there. This is why we call it trigonal pyramidal. Here. Ammonia. That's a nice trigonal pyramidal. That's not exactly right. Here again, they're including the electrons here, but trigonal pyramidal. How about amide? Take a look at amide. Amide's going to look a little bit different. when we look at just the atoms, it has a V shape to it. It's like water. You know, water is very similar to this. Actually, if we look at the Lewis structure of water, water is H2O, so it's an HOH, and then there are two lone pairs to complete the octet. So water looks exactly the same as amide, and so it has a V shape to it. The atoms have a V shape to it. The electrons have a tetrahedral shape, actually. So let's take a look at some more amide. The Lewis structure of amide using dots instead of lines. Here are the three that we're doing: ammonia, ammonium, and amide. We're good. Amide's got a negative formal charge. You know, usually circle, so you can show it circled in here, and then we do the square bracket so we can sum up the charges. This is potassium amide. I guess that was it. All right, did you guys calculate the oxidation states in the formal charge for amide? Or do you need more time to do that? You got the oxidation states? Okay, tell me the oxidation states. Okay, -3 on color here. So oxidation states. So we got -3 on nitrogen and +1 on the hydrogen. And those have to add up to -1, do they? Yeah, +1, -3 is -2, +1 is -1. So they add up. What did you get for the formal charges? 0, minus, -4, -3.
I said -3, but because of that extra electron, so I don't think it's
-4? Okay. All right, -4 and
0.
could this be correct? It can't be correct because it's 0 plus a -4 plus a 0 should equal the -1, so it can't be correct. It's got to be 0, -1, 0. Now where did that -1 come from? Yeah, right, because let's count it. We're going to split it 50-50. So it's 2, 4, 5, 6. So nitrogen ends up with 6 electrons in the structure. How many did it contribute? 5. And so it ends up with an extra electron, so it's minus. So those would be the oxidation states on the top, the formal charges on the bottom. Did everybody get that? No? Do you want some more practice with oxidation states and formal charge? We'll do some more practice with oxidation states. Methane is also tetrahedral. You know, methane's got a nice tetrahedral shape to it, like ammonium does. But I'm not going to draw a tetrahedral. Lewis structure, we don't care. And here, if I wanted to draw this as a tetrahedral, it would look like this. I put a carbon here. One of the hydrogens I put in the plane. The other hydrogen I put in the plane. This one I'm going to stick out like this. This one's going to stick in. That's what it would look like. But what would the oxidation states here be? It's winner take all. Remember, oxidation states winner take all. Yeah, that's right. And so the carbon would be what? +4 or -4? The hydrogens are +1. Okay, if the hydrogens are +1, then the carbon must be -4. -4. So is methane electron rich or electron poor? What would you classify it as? Electron rich. It should burn, right? And so redox properties, we want to look at the oxidation state. Okay, then what we're going to do is we're going to go and look at the formal charges. What are the formal charges on it? It'd be 0 on everything, yeah. All the formal charges are 0. I'll write it on this structure. Everything is 0. Okay, I'm going to go to this one next. We're going to look at this. Do you know what this molecule is? No. Well, ethanol. Ethanol. It's a 2-carbon alcohol. I can tell it's an alcohol because of this COH here. It's ethanol. Okay, why don't you do the oxidation states in the formal charges for ethanol? Remember what I did. If you're having trouble starting, remember what I did as far as winner take all or 50-50. Winner take all is like this. Carbon gets that. 50-50 split is like this. Shared. So you got to split up the electrons that way and then count them. So, carbon versus hydrogen, we're doing oxidation states. Carbon versus hydrogen, who wins? However, carbon versus carbon, who wins? Well, if carbon wins, then there is no winner take all, carbon versus carbon, because we got to split it. I mean, carbon versus carbon is, both are going to win, I guess. And so then we count it. We count the electrons. 1, 2, 3, 4, 5, 6, 7. If it has 7 electrons, well, how many did it contribute? It contributed 4 valence electrons. Carbon has 6 total electrons, but it only contributed 4 valence. So it ends up with 7, so it came out with how many extras? 3. So it's -3. So that carbon's -3. And the hydrogens are going to be +1, all of them, because they end up with nothing. Okay, then we go over here. Carbon versus hydrogen, who wins? Carbon. Carbon versus carbon, well, it's going to be a tie. Carbon versus hydrogen, carbon wins. Carbon versus oxygen, oxygen wins. And so let's count them. 1, 2, 3, 4, 5. Carbon ends up with 5 electrons here. How many did it contribute? 4, so it ends up with, yeah, 1 extra. So this carbon is -1. This oxygen is, well, oxygen versus hydrogen, oxygen is going to win. So this oxygen is 8. And how many did it contribute? 6. So it ends up with 2 extra. So -2. These hydrogens are +1. And this hydrogen will be a +1 because they all end up with nothing. Okay. And so, is ethanol electron rich? Would you say? Yeah, I'd say because this, especially this carbon here, electron rich. This one's somewhat electron rich at -1, but this one's quite electron rich. So, do you expect ethanol to be flammable, to burn? Yeah. What about the formal charges? So formal charges, to do them both on the same structure will get messy. So we'll just do formal charges on a separate structure. But why don't you try that? I'm going to end early today because I have a lunch appointment I got to make. So we'll start up. We'll do some more tomorrow. Formal charge, oxidation state, Lewis structures, and shapes tomorrow. Okay.